Flack math! Give me some math and I'll give you some flack. Flack math!
We're going to talk about coordinate proofs. We're just going to do one lesson today, so we can do this. This is going to be intro, just an intro to coordinate proofs. So this is just using the coordinate plane to help prove something, okay? All right, so basically you can write that definition if you want, but a coordinate proof is a style of proof that uses coordinate geometry and algebra. The coordinate proof diagram is used that is placed on the coordinate plane. So it's good to be strategic about how you position a shape on a plane. So for example, look at example 1 here. So if I want to say triangle ABC has a base of 4 units. So if I want to say triangle ABC has a base of 4 units and a height of 3 units. Okay, and then I wanted to say A is a right angle. Okay, so if this is what's given, I would be strategic and I'm going to put my 4 units right there and my height of 3 there. And then I'm going to call this A because that's my right angle. So then it's easy to see. Okay, yeah, that has a base of 4 units because it goes over 4 from the origin. And then it has a height of 3 units, so it goes up 3 from the origin. So it's nice to be strategic. Like this is kind of a bad way to do it. If I just had coordinate plane here and then I had a right angle there, A, B, C, that's not going to be very easy to prove any point, okay? Because that's a lot of math that you don't have. So try to eliminate as much distance calculating and everything. So see how this is a better place to put that. This is a dumb idea, okay? All right. So when it's placed in a convenient position on the coordinate plane, the equations and values used in the proof will be easier to work with, okay? So there's going to be some questions on a test that say, okay, put this on a coordinate plane that would be the easiest to work with. So I'm going to show you like 4 different examples of good places to put shapes so you don't have to worry about confusing equations and math calculations. It's just easier. So here's another way to do it. So this is a good place to do it. So if it's right on that plane, on that line there, then it tells you, then you can see exactly what that base is. You can also see exactly what that height is. I would do that other than this. If you did this, then that's okay. But see how you have to still do the math to figure out the length of that base. If this goes over -2 and over +2, see how you still have to do the math. That's 4. 2 + 2 is 4. But if it was like this is a better way. This is not as ideal. Okay? This isn't bad, but just try to eliminate as much of that math as you can. Okay? All right, so here's another one. So see how this is, you can know right away what your length is, or what your base is and what your width is, if you place it there. If you place it somewhere in the middle or something like that, then that's just not a great idea. So for example, if you put your rectangle right here, that's okay, but you still have to do the math to figure out like what your height is and what your length is. So just make it as easy as possible. So you can kind of see that it's nice to have a vertex, some vertex somewhere on the origin, okay? Okay, yeah, and then here's like another one. They did do this. I mean, this is, I would rather just move it over, but that works too. And then here's like another one. So see how that is like right there, so you can kind of see the height. It's depending on what you want to prove. If you're working with area and stuff like that, it would be nice. So see how this can still tell you the length of that base and the height of that triangle, okay? All right. Still not quite done. Sorry, Tori. Okay. Good effort. Okay, so here's an example of a real life proof that we're going to use the coordinate plane to prove. Okay? Oops. All right, here is example 2. We're going to show that triangle HIJ is an isosceles triangle. Okay, and here's what the coordinate looks like, the coordinate plane looks like. Okay, you guys see that? So this is actually part of your given statement. So I could say that the length of this base, if I wanted to, I don't really need to because I'm proving something that has nothing to do with the base. I could say the length of this base is given that it's 6 units. Okay, so I could say given so HIJ. Okay, so I could say what's given is HI equals 6. I could say that the height equals 2. The height of the triangle, the altitude of the triangle is 2 units if I wanted to, because that's what's on the coordinate plane right now. But I don't really need those for what I'm trying to prove. What do I have to prove that this is an isosceles triangle? What? Good question.
One side the same, two sides.
Yep, so I need to prove that HJ and JI are the same length. Okay, so this is what I'm trying to prove. I'm trying to prove that HJ equals IJ. Right? That's what I'm trying to prove. The only thing I'm given is the actual coordinates of H, I, and J. So here's what's given. H is 0, 0. I is, what is that, 6, 0. And J is 3, 2. Okay? So this is going to make my calculation of distance a lot easier because of these zeros and things. It's going to just be easier. So I need to prove, so I'm going to say given, basically that what's given there is H is 0, 0, 0, I is 6, 0, and J is 3, 2. Why? Because it's given. Okay, now what should I do next? Yep, calculate the distance. So HI, or HJ, right? HJ equals the square root of the difference of
It's
x's squared.
minus y2 and 1 minus x2.
Yep, so 3 minus 0 squared plus 2 minus 0 squared. So this is the square root of 9 minus 4 is 5. Why? Because of the distance formula. Okay, so the square root is the square root of 5, which is an uncomfortable number, but we don't care because all we need to do is prove that HJ is the same length as IJ. Well, let's find IJ. Well, what's IJ? That is the square root of, let's see, I is going to be 6 minus 3 squared, and then the y's are just going to be 0 minus 2 squared. So then this is going to be 9 minus 4 as well, which is the square root of 5. So I can put all that on one line because I'm just using the distance formula right now to figure out the distance. So I'm going to say 3 HJ equals IJ because they both equal the square root of 5. So if they both equal the same thing, they equal each other. What property is that? Well, not reflexive. Reflexive is like Tobin equals Tobin. Transitive, right. So if HJ equals the square root of 5 and IJ equals the square root of 5, then HJ equals IJ, okay? Or substitution. Because the square root of 5 equals IJ. So if AJ equals the square root of 5 and the square root of 5 equals IJ, then HJ, see how the transitive and substitution are kind of the same, you can kind of use both. So number 3 is transitive or substitution prop. Okay? So we just used a coordinate plane to prove that. So that's all we were given. So if this was all we were given, show that HIJ is isosceles, we have no idea what HIJ is. But we're given a coordinate plane with a triangle on it. So we have to prove, okay, so now we can use the coordinate plane as what's given to us. Okay? Now they both look the same, but we have to prove mathematically and geometrically that these two are the same length. And we just did, using the distance point. Okay. So far, so good? All right. There's more. Yes, it's a gift that keeps on giving. Okay, so sometimes a figure's dimensions might be unknown. When placing a figure with unknown dimensions on the coordinate plane, pick a convenient position and label the vertices of the figure using information that is given in the problem. So we might not have, so if we draw a coordinate plane like this, and we have a rectangle here that looks like this, maybe. Or maybe it's a square. If it's a square, then let's see. If this is 0, 0, right? This is 0, 0. Then this would be some point, like maybe A, comma 0, because it's still on the x-axis. So see how this would be A0. And if it's a square, that means this is a 0A, and this would be AA. Okay? So if it's a square, we can put it on the coordinate plane like this, where A can be any number. Doesn't matter. Okay, so this is example 3. A square has a length of A. A square has a side length of A. Place a square in the coordinate plane and label each vertex with an ordered pair. So that's just the solution. So here's example 3. A square has a length of A. So see how this is A long because it goes from 0, 0 to A0. And this is A high, so it goes from 0, 0 to 0A is the second number, and the coordinates is the height. And then this guy is over A, up A, right? So see how they all have a length of A. So if you drew a, so it wouldn't make sense to do something like this. This is a bad idea. Because you can say like this whole length is A, so this is, so now you can't even label these because the whole length is A, and if it's halfway, maybe you could say 1/2 A, 1/2 A, 1/2 A. Well, that doesn't make sense. So just put one of the vertices in the corner, in the origin. So then this is A, so it goes from 0, 0 to A0. All right? Okay. Let's do another proof for 2. And then we can call it good. All right, here's example 4. Here's what I want to do. I want to, given parallelogram OPQR with one side length labeled C, with one side length labeled C, assign possible coordinates to the vertices. So this isn't a proof. We're just trying to put it on a coordinate plane. Assign possible coordinates of vertices. I know, except it's a parallelogram, so we don't know. The only thing we know that it kind of looks like this. So if I drew a parallelogram, just a generic parallelogram, it would kind of maybe look like this. Boom, boom, boom. So if you see what I did put one vertex in the origin, which is always good practice. So we have no idea. We just know that one side length is C. So we can either choose this is C or this is C. I'm going to choose this as C. Okay, so what is this vertex? What's the coordinates of this vertex? What is that? 0, 0. Okay, so that's 0, 0. What about this one? Except it's backwards because C is left or right. This is left or right, so it's C0. Now what about these? Well, these are a little different. So we need another variable because we don't know this height and we don't even know this length. So we have to say maybe like over B up D. See how we did that? So we don't know either of those. But if this is over B up D, then what would this be? Well, first of all, so this is over B. So like over here would be like, this is a length of B. Okay, but what would this length be? What would be here? Well, first of all, we do know the Y. What's the Y value of this? It would be the same as this Y value. It's the same height as that one. So it would be something D. Okay, but what is that X value? You have to do a little math or variable math. So what is the distance from here to here? Well, that's C, but what's the distance from here to here?
C plus B.
C plus B. Okay, so here's C,
Because it makes
and then this is B more because this was B. Since it's a parallelogram, go with your gut. It's this length here, that's B. So this length is also going to be B. So that's C plus B, or B plus C. Okay, so that was a little weird, but see if you can label the sides. It's like, so this, it wouldn't do anybody any good to label this side, right? I mean, you can label that A if you want, but see how that A length doesn't help you with this coordinate. Because this coordinate represents this length and this length. So this length we're just saying is B, and this length we're saying is D. So the height of that is D, so the height of this has got to be D. Boom, that's done. But this one is all the way from here to here is C plus this length, which is the same as this length, which we decided it was going to be B. Okay? So a little crazy, but do it. All right, let's do another one like that. This is 4C. So this was example 4A, 4B, and now we're on, oh, these are 3, sorry. Example 3. So this is 3B. Sorry, if that's important to you, I'm sorry that I messed it up. Okay, so here's a coordinate system, coordinate plane, and here's what they ask us to do. They want to say assign coordinates to the vertices of an isosceles triangle STU with a height of 4 from the vertex. So isosceles triangle STU with height. This is an iso triangle, which is an isosceles triangle with height of 4. What would you like to do here? How do you want to draw this? An isosceles triangle with a height of 4. What's going to be the easiest way to do this? Okay, so it's going to be 4. So you can do that. Yep. So you could do this, and this is probably what most of you will do. And so this length is going to be, I don't know. I mean, this is going to be the same as that. So if this was like A, then this would be 1/2 A and 1/2 A, and this would be like B. Oh no, this is 4, right? So then this would be like 1/2 A comma 4. Let's not do it this way. All right. So here's what, since it depends. It depends on what you're trying to prove. Okay. Now, if I was trying to prove area or something, it'd be nice to know, have it like that. But I'm not. So here's what I'm going to do. I'm going to do this. I'm going to say that my triangle 2, 3, 4 is right here. So now I can say, since I know on an isosceles triangle, these two have to be the same length, now I can just say A. So what are the vertices of this triangle? What's this vertice on the right here? What's that vertex? What's the coordinate of that? How much over to the right and how much up or down do you go? Okay, we'll come back to that. What about this one? What's the coordinates of this point, that top point? That's the height. So remember the height goes second. So what comma 4? 0, because it doesn't go left or right at all. So that's 0, 4, right? Okay, now how much right does this vertex go? Yes, we don't know, but we choose the variable. Choose isn't a word. So A0. And what about this? Not the same. Negative A0. Okay, so see how this would be a little bit easier. You can do it this way if you want, but see, that's going to force some fractions. 1/2 A and 1/2 A or whatever. So I would just do it like this. And that way you can clearly see, oh, those are the same length and you just have to choose one variable. There's not a wrong, I mean, this isn't wrong to do it this way. It's just more complicated. Okay. All right, so last example is just writing a proof, a coordinate proof. So that's what we're going to do last, and then we'll call it good. And I'm just going to mention our life application example. I've been skipping over those, but then I felt a little guilty about it because I like my math and my isolated. Let's keep math safe in a place where we never have to use it. No, not that. But I like that kind of math where it's, that's why I don't really like physics. Don't tell my brother.
I don't like it either, don't worry.
I don't like that kind of math because it's like actually math that you would use if you really wanted to, type of thing. But
I don't like it either, doesn't make sense.
well, sometimes physics in general just doesn't make sense.
Yeah.
That's what makes it so cool
No, like,
from a distance.
it's like algebra 2 on the track.
Okay, so here's example 4. So I'm going to write a coordinate proof, and I'm going to prove that diagonals of a square are perpendicular. Okay, that seems a little overwhelming, but I'm going to just try this. So, any suggestions on how to draw my coordinate square? Where should I draw my square? Yep, okay. So then I'm going to go like this. So what are the coordinates of each of these vertex? So this is 0, 0, right? What about this? Yeah, so let's say A0. What about this? A, and then this is, everyone good with labeling that? Does that make sense? Because if the distance is just A, then this would be A0 because you're going over A, and then up 0. This is you're going over A and up A, okay? All right. So here's how I'm going to prove it. I need to prove that these diagonals are perpendicular. How do you prove that lines are perpendicular on a coordinate plane? You guys know how to do that?
Oh, it's,
What do you know on a coordinate plane or in algebra? How do you know that lines are perpendicular? By just looking at the equations of the line. What? Yeah, but you can't really prove that on a coordinate plane. How do you prove it algebraically? How do you prove that two lines are perpendicular algebraically? What? We're going to use the vertex, so that'll be part of it for sure. Okay, so try not to think about the shape of a square or anything. Just try to think about lines that are perpendicular. Now think back to algebra. What do you know about lines that are parallel in algebra? So perpendicular lines are right angles, but you can't prove that algebraically. Same, parallel lines have the same slope. That's right. Okay, now, do you guys remember what perpendicular lines have? They're not the same slope, but you flip it upside down and you negate it. So there's like two types of opposites for perpendicular lines. So for example, parallel lines have the same slope. So M equals M. So M1 equals M2. So remember, M is the slope, Y equals MX plus B, all that stuff. We're not going to totally get into that, so don't worry about that. Perpendicular lines, you flip them upside down. Perpendicular lines have negated reciprocated lines, negative reciprocal slopes. Reciprocal means you flip it upside down, and negative means you change the sign. Okay, so for example, M1 equals 1 over negative 1 over M2. So if we can prove this, then we can say that they are perpendicular. Now, we have coordinates to work with. How do you calculate slope between two coordinates? Rise over run, okay? So what is the slope? Let's make these different colors here. Did you? Good job. Okay, so the red line. So how do you calculate that? So M equals rise over run. Remember, the slope formula is x1 or y1 minus y2. That's rise. That calculates rise. The distance between the y values is how much it goes up or down. The distance between the x values is how much it goes left or right. Okay? So in M1, so let's choose, it doesn't matter which one you do first. So how about we do, what do you want to do first? Let's do this first. So let's see, y1 minus y2. So a minus 0 over 0 minus a. So do you see what I did? So the y values is a minus 0, because those are the y values. And then the x values are 0 minus a. So what does that equal? A minus 0 is a. What's 0 minus a? What's 0 minus a? Negative a. Okay. So let's come back to that. Now let's do the green slope. What do you want to do? What's our y1 or whatever? So we're going to go a minus 0, which is that. And then their x values are same. You have to start with the same one you started with the y's. A minus 0 again, which equals a over a. So are these flipped over and negated? Yeah, they are. So QED, whatever. So since a over a is the negative reciprocal of a over negative a, then perpendicular slopes, perpendicular lines, or perpendicular slopes. Okay? So you just have to prove, or if you simplified this, this would be -1, and this would equal +1. So what happens when you flip over 1 and you negate it? It's just -1, right? In order to flip something, it has to be a fraction. So how do you write 1 as a fraction?
Oh, 1 over 2.
1 over 1. So when you flip it, it's -1 over 1. Simplify it, -1 over 1 is just -1. Okay? All right. That's basically it. Let me just walk through our application in our life application here. Yay. Okay, look at this. So exciting. Constructing a swimming pool. Can you guys see this okay? So we're just going to walk through this. We're not going to spend too much of our brain on this. Let's just walk through it. A contractor has been hired to build a swimming pool with a smaller wading pool beside it. And so most contractors would use graph paper to be able to map out, or architects do the same thing, so to design what they want. So hired to build a swimming pool with a smaller wading pool beside it, the contractor draws a diagram of what he plans to build and overlays a coordinate grid on it as shown, okay? So The wading pool has a surface area one that is 1/8 the size of the larger pool surface. Okay, so it looks like you did a little wading pool, a little triangle there. Do you see that? Okay, so is that 1/8? It looks like 1/8. So the area of the triangle is length and width. Is length times width. So if this is C and this is D, so C times D, that would be CD. So the wading pool has to be 1/8 CD, right? Well, let's see if that's the case. To find the area of this triangle, it's base times height divided by 2, or 1/2 base times height. Okay. So here is the 1/2 of this would be 1/2 of this whole thing would be 3. So times the height, which is 2. Is this drawn incorrectly? It's 1/8. Yeah, because it's 2/3 of it. So how do you find the area of that triangle? Well, 1/2 of that, so that's just C over 2. So 1/2. Oh my goodness, that does not. Oh, that's right. That's right. That's right. That's right. That's right. C over 4. Got it. D over 2. That is not D over 2. See why that's not D over 2? See how that's drawn incorrectly? Anyone else seeing that? Because if this is D up 3 units, right? 3-ish units, then this should be kind of right there. But we're not going by the 3 or anything like that, so I guess it kind of makes sense. It doesn't make sense visually, but. So to find the area of that, it's 1/2 base times height. So C over 4 times the height of that, which would be D over 2, which would be 1/8 times CD, or CD over 8. Okay, that's 1/8 CD, which is the area of the swimming pool. So that works. Okay, that's it. That's all I got. Good job. Well done. Good and faithful students.